So basically, today we are going to learn what is paramagnetism, what is the possible origin of paramagnetism, what is ferromagnetism, what is the possible origin of ferromagnetism, and uh, there will be something called hysteresis loop, which is actually uh, shown by this hysteresis actually exhibited by ferromagnetic material. So we'll discuss this hysteresis loop also. Okay. So basically we'll learn what is paramagnet, what is ferromagnet, and then what is hysteresis loop, etc. So let us start our class today. So I hope you people are able to see my screen. Just I think it's so we can discuss some of the like questions, like possible questions on this chapter also, if time permits. Oh, it is actually a bit slow. Just excuse me for that. Um, do you see my screen? Are you people able to see my screen? Okay. Um, okay, so let us start. See, in the paramagnetic material, you have actually what is called permanent atomic dipole moment. Permanent atomic dipole moment. Okay. So you can just okay. Okay, you can see that. Okay, fine. I actually my screen is not shared yet. Just a minute. I'll just open my presentation. Okay. Suddenly it got okay. Just a minute. I'm just opening my presentation. Yeah, please excuse me for this. Actually, it is sometime it gives some trouble. Okay. Okay. I hope this is another presentation. The one I opened actually actually that got freeze somehow. Okay, anyway, so let us start our original discussion today. So what we'll discuss is actually, first let us discuss paramagnetism. Okay, we'll discuss paramagnetism. First let us discuss paramagnetism. Okay, so see, let us see a paramagnetic material, what is there inside. So like paramagnetic material, inside paramagnetic material there are atoms. Obviously in any material there will be atom. So in paramagnetic material the atoms actually the atoms have their net dipole moment. Okay, each atom they have net dipole moment. Okay, each atom they have net dipole moment. But the thing is, this dipole moment, so you might be thinking what is this dipole moment about. Okay, actually this dipole moment is not due to orbital motion of electron. This is actually due to unpaired electron. Unpaired electron, you might be thinking what is this then. I'll tell you what is this. So unpaired electrons, so this dipole moment is due to atomic dipole moment due to unpaired electrons. So you have all the orbitals, right? S, P, D, F, etc. Okay, so S can accommodate 2 electrons when it is completely full. Then when P is completely filled, it can accommodate 6 electrons. D can accommodate 10 and this can accommodate 14. But suppose you have electron numbers not sufficient to fill all S, P, D, F. Okay, suppose if I take iron, or iron is not a paramagnet. Okay, let us take something else, manganese maybe. Okay, so iron, manganese, or anything you take, you'll see that in case of, at least in case of iron, there will be obviously this Ap3 plus, there will be D5 electrons. Okay, there will be 5 electrons. Actually in the D there should be 10 electrons, but there are, see, there should be 10 electrons, but see, like this, there are 5 electrons. This is half filled. So when it is half filled, what happens? It has net dipole moment. So this dipole moment is not due to orbital motion of the electron, but it is actually due to the spin. Due to the spin. See, each electron while revolving around the nucleus, around the nucleus, it has its own spinning motion as well. So spinning motion, okay, around its own axis. So due to the spinning motion, it has a dipole moment which is denoted as mu s. Okay, in this chapter we have learned, see, not in this, the previous chapter we have learned orbital magnetic moment denoted by mu l. So now you see in this paramagnet or ferromagnet, so this magnetism is arising due to the net, see, the dipole moment arising in an atom due to unpaired electron, or maybe some complicated reason, so which is not so much like discussed in your textbook. So you know so this is due to the spin of electrons. This is called spin of electron. You might be knowing from your chemistry uh, knowledge. So spin of electron. So there are 4 quantum numbers: principal quantum number, then magnetic quantum number, spin quantum number, and azimuthal quantum number, something Z. Okay, there are some 4 quantum numbers are there. So this is actually from the quantum theory. Okay, this is not a classical theory. So what happens? You have, see, unpaired electron in your materials. So you might be thinking that if this is arising from spin, and if it is from unpaired spin, if the spins are paired, what would happen? See, spin, electron spin, there are the up and down spin, right? We say up spin and down spin. Like this, it is full for a particular orbital. So see, when electron orbit like this, okay, like around its own axis, suppose this is up spin, and then when electron just spin around its own axis in this way, so suppose the spin is down. So if both the pairs are there, then see, for this case, suppose the magnetic moment is this down, and for this case magnetic moment upward, okay, upward mu s. So this up and down magnetic moment, dipole moment, we generally denote by this. Dipole moments are actually denoted by a straight line with an arrowhead. So this is magnetic dipole moments for a pair of electrons. See, these two will actually have same magnitude, but they will have different, exactly opposite direction, and these two are vectors. So these two vectors will be cancelling each other for a atom. For an atom, when you have fully like field electron orbitals, okay. So for a paramagnetic material, their atoms have unpaired electrons, okay. This is what I wanted to say. So the origin of paramagnetism is unpaired electron. So if you have all the atoms having unpaired electrons, so they have certain magnetic moment, suppose denoted by mu s. And see, we have defined magnetization is equal to the net magnetic dipole moment, net magnetic dipole moment per unit volume. Okay, so this is the definition of magnetization. So when you have of the order of 10 to the power 23 or maybe more than that electrons, so you will get a good amount of net magnetic dipole moment and magnetization. But the problem is, in case of paramagnet, these atomic dipoles, they actually don't cooperate with each other. They don't cooperate with each other. So what they do, one dipole moment would like to be in this direction, other maybe like this, or maybe another maybe like this. Okay, so they actually orient themselves in a very utterly random orientation. Okay, when you have vectors, like vectors oriented in all possible random direction, when you take the average of them, so what you get, net magnetic dipole moment, you will get actually zero. Okay, net dipole moment will be zero. And see this, or what is the reason for this random orientation for them? So the dipole moments actually, uh, when the temperature is large, or maybe at room temperature also, the paramagnetic dipole moments, they have certain energy called kbt. This is the thermal energy. This thermal energy will actually make this dipole randomly oriented. Okay, ceaseless, it is said that ceaseless thermal uh, vibration. Okay, this is because of the uh, thermal vibration, or because of the temperature, they have thermal energy, and this thermal energy will not allow them to orient in a particular direction. Okay, so when they orient in a particular direction, then only we will get net magnetization, okay, or net dipole moment. Look what happens. So we have seen that paramagnetic materials, they have like all the way like randomly oriented dipole moments, magnetic dipole moments like this. So when you apply a strong magnetic field B0 from outside, so what will happen? The dipole moments will try to orient in the direction of the field. If it is really very strong, very strong, very strong, and the temperature is low, sufficiently low, then what happens? All the atomic dipole will be oriented in the same direction as the applied field. Okay, applied field. So when they align in the same direction, then you get a net dipole moment m net, and then if you divide it with volume, so you get magnetization. This is called magnetization or intensity of the magnetization. So you can understand that paramagnetic, they have actually permanent dipole moment. Permanent dipole moment. What they have? Permanent dipole moment. But because of thermal motion, because of thermal motion, they are oriented in a very random directions. Okay. And one more thing is actually they don't cooperate with each other. They don't talk to each other. This dipole moments, they don't talk to each other. Okay, they don't have any relation. So if some guy is in this direction, other guy doesn't care whether it is in this direction or any other direction. So that the other guy will be just uh, like be with his own what to say, ego. Okay, they don't talk to each other, they don't cooperate. So this is actually called independent spin. Okay, these are called independent magnetic moment. So in the paramagnetic case, the magnetic dipole moments are independent of each other. They don't cooperate with each other. Okay. So this is the origin of paramagnetism. Okay. This is the origin of paramagnetism. Now I'll tell you one thing. So in this case, you know, the paramagnetic material, they have mu r greater than 1. Okay. And it is positive. Obviously, chi also, in this case also, the chi is positive because it is greater than 1. Slightly greater than 1, it says. Slightly greater than 1. So this is chi is positive. Chi positive means, so mu r means what? Relative permeability. That means if you uh okay, or if you have a paramagnetic material which you are placing in a place where there is a magnetic field, uniform magnetic field. So what will happen? This, see, suppose there is a magnetic field here. So this paramagnetic material will try to concentrate the dipole moment, this sorry, magnetic field lines inside the material. Okay, inside the material, it will allow. So permeability means it will permit the magnetic field lines to pass through the material and thereby induce a magnetism, or get some induction inside this material. Okay. So in case of diamagnetic material, we have seen that they repel the field lines. Okay, they repel the field lines. They don't allow magnetic field lines to pass through them. Okay, field lines will go like this. They will repel the magnetic field lines like this. Okay, don't allow. So I'll just draw once again. See, I'll just draw. This is dia magnet and this is para. So what is the difference? See, the dia will not allow any magnetic field lines to pass through or go through them, because like that. Okay, so this go like this. Okay, and outside it will be like this. So hardly one or two magnetic field lines may go inside, because see, the chi is minus. Chi is minus means the diamagnetic material will repel the magnetic field lines of external magnetic field. Okay, but in case of paramagnet, you know what they will do? Paramagnet will be actually passing through this material. Okay, passing through the material, passing through the material. This paramagnet will try to attract magnetic field lines through them and thereby induce a magnetism inside them. That's why when you keep a diamagnetic material, see, suppose there is north pole and here is a south pole. Okay, So there is magnetic field lines in this direction, as you know. Now, if you just suspend a diamagnetic material, suppose in this direction, if you just suspend a diamagnetic material, immediately it will be rotated perpendicular to this field lines. Okay. So what will happen? It will actually be aligned in this direction. Okay. Immediately this gets aligned in this direction, perpendicular to the magnetic field. So why is this? Because see, diamagnet will repel the magnetic field and it will try to orient in the low field direction. Okay. Try to orient themselves in the low field direction. Okay, this is the case. Always oppose the magnetic field. But if you keep a paramagnet, what will happen? Paramagnet will actually, if you keep any other orientation, they will try to be with this. Okay, in the same direction as the applied field. Okay, field of this electromagnet. So this is a para, and thereby this material will get induced with magnetism. Okay, that's why this. Uh, if you if you have a uniform non-uniform magnetic field somewhere in some region, suppose here it is strong, magnetic field is strong, b1 here b2, non-uniform magnetic field. Okay, b1 is greater than b2. So if you keep a diamagnetic material, what will happen? This diamagnetic material will go from strong field region to weak field region. This is a dia. This is a dia. Okay, but in case of para, what will happen? Para will actually, if you place it anywhere, it will always try to move from low field side or weaker field to stronger field region. So from B2 to B1, this way it will move actually. Okay, because it attracts the or allow the magnetic field lines to pass through them and get induced by external magnetic field. Okay, okay. So another point is, see, diamagnet does not depend on temperature. If we increase the temperature, it does not depend. Okay, does not diamagnet does not depend on temperature. Okay, but paramagnet, so this is dia, but paramagnet, that depends on temperature. So the magnetism in paramagnet depends on temperature. We'll see how it depends. See, magnetization in paramagnet, I'll write here para. It is proportional to the external field applied. Okay, and it is again proportional to, actually inversely proportional to the temperature of the material. That means if you increase the field higher and higher, you will get more and more magnetization in paramagnetic material. But if you increase the temperature, then what you get is lower and lower magnetization. So that's why we say, if the temperature is lowered and applied field applied field is increased, I'd say this decreased. Lowered means decreased and applied field increased, then magnetization in paramagnet will saturate. Magnetization in paramagnet, saturate means what? I'll tell you. Will saturate. Okay, what do you mean by saturation? When, see, in your paramagnetic material, all the dipoles are already aligned in the direction of field. then there are no further dipole moments to align in the direction of field. So in that case, you know what will happen? The magnetization will not increase further. That is called saturation magnetization. Okay. So in paramagnet, generally saturation does not occur in very low field. You have to give a very large field. Okay, very large field, and you have to take it to low temperature as low as actually 5 Kelvin, 2 Kelvin, etc. Then you get saturation magnetization for a paramagnet. So if we combine these two dependence, field and temperature dependence, so we can write this as actually C H by T. Okay, C H by T, or we can write chi is equal to C by T. Okay, so this is called actually Curie law. This is called Curie law. What is this called? Curie law. This is magnetic susceptibility, which I have written M by H. M by H is chi. Sorry, M by H is chi. M by H is chi. So this is actually Curie law of paramagnetic susceptibility. If you draw the graph chi versus t, okay, you will get typically this, okay, hyperbolic curve. Okay, because see chi and t, this is constant. This is c is actually a constant called Curie constant. What is this called? Curie constant. Pierre Curie had done a lot of research on this magnetic material, paramagnetic material, basically, and had given this law: temperature and field variation of uh, magnetic susceptibility can be expressed in this way. So this is the case, and if you draw, see sometime in case of paramagnet, so I'll show you some card. So this is actually for paramagnet. If you draw chi and t, but if you draw 1 versus chi and t, you will get a straight line like this. Okay, straight line through origin. Okay, it is a straight line through origin. You'll get straight line, sorry, straight line through origin like this. Okay, this is for paramagnet. This is temperature and this is chi. Okay, I think, yeah, I have already denoted. So these are few carbs, and you know, like sometimes there will be a question. So suppose there is a paramagnetic material, it has susceptibility chi 1 at certain uh, like 20 degree centigrade. Some susceptibility will be given. Okay, 20 Kelvin, 27 Kelvin, and susceptibility when suppose this is okay, so chi 2 is equal to 2 chi 1, then what is the temperature? Okay, what is the temperature, at what temperature? I'll just give you the correct question. Let us see whether you can get some idea about this. Just a minute. So there is a question that susceptibility of a paramagnetic material at 20 degree centigrade is actually chi. Okay, this is, okay, susceptibility of a paramagnetic material at 27 degree centigrade is chi, and at the question is at what temperature the susceptibility of the same material will be will be chi by 2. Okay, chi by 2. So this is the question. So how to do that? We'll be using the Curie law. We know Curie law is actually chi is equal to c by t, or this implies chi t is equal to constant. Okay, constant. So I can write chi1 t1 is equal to chi2 t2. Okay, so now you have to find out t2. So you write chi1 t1 by chi2. Look here, this T actually is the absolute temperature, absolute scale, not degree centigrade. Whatever temperature is given, you have to add 273. So here the temperature T1 is actually, so look here, chi is given chi, and here chi2 is chi by 2, and this temperature is 27 degree centigrade. That means it is actually 300 Kelvin. So it is in Kelvin temperature. So this T in the Curie law, it is in Kelvin scale. That means if you are given some temperature, suppose theta degree centigrade, then you have to add 273, okay, along with that to get Kelvin in Kelvin unit, okay. So I have added 273 with 27 degree centigrade, then I'll get 300 degree. So look, what I can do is, okay, yeah. So what I can get from here, I'll just clean everything. So chi 1 by chi 2 into t1. This is the relation now. So chi 1 is given chi, this is chi by 2, and this is 300 degree, sorry, 300 Kelvin. So from here you will get Kelvin. Susceptibility, these are unitless or dimensionless quantity. So you look here, it is 300 into 2, so this is 600 Kelvin. So now you have to express this T2 temperature in degree centigrade. So you have to again subtract 273 Kelvin. So finally what you will get actually there, this is the degree centigrade. Okay, this is the temperature when your susceptibility will become chi by 2 if at the temperature to 27 degree centigrade the susceptibility is chi. Okay, this is how you have to use Curie law. Alright, so let me just go to ferromagnetism now. So in case of paramagnet, we have seen that they have dipole moment, atomic dipole moment, but they don't cooperate with each other. But in case of ferromagnet, you know, they have permanent dipole moment, exactly like your paramagnet. But along with that, there is a certain property extra. We'll discuss it here, like that. So you look here, what will happen in case of ferromagnet, the dipole moments cooperate cooperate with each other, cooperate. So they cooperate. That means if one dipole moment is in this direction, it will try its nearby atomic dipole moment to bring with this, okay, in the same direction. So in case of ferromagnet, the permanent dipole moments will try to orient themselves along with each other, okay, in the direction along with each other. And you know, in the absence of magnetic field, what will happen inside a ferromagnet there will be a micro regions, okay, micro regions, very small regions, where the atomic dipole moments will be oriented in the same direction, in the same direction. So here maybe this way, So these microscopic regions are called actually domains. Okay, these are called domains. So ferromagnetic materials are having magnetic domains. Okay, they are having magnetic domains. So these small regions are called magnetic domain. Okay, and the wall or separation between two domain is called domain wall. See this one. This is called domain wall. So it is separated from the other domains. These are other domains. Suppose here the field like magnetic domain like magnetic dipole moments are upwards. So like this. So you have in a ferromagnetic material called domains where the atomic dipole moments they cooperate with each other and try to orient in the same direction. Okay, and you know what will be the typical size of the domains of the order of 1 millimeter. Okay, 1 millimeter. But how many atoms will be there in single domain? Of the order of 10 to the power 10 atoms will be there. 10 to the power 11 atom almost in each domain. In each domain. So see, each domain they have certain net dipole moment because in each domain, individual domain, they have net dipole moment. Okay, net dipole moment because in the same domain all the spins are oriented in the same direction. Okay, they cooperate with each other, they interact with each other. Interact means they talk to each other. And how do they talk? Actually quantum mechanical phenomena, it is called quantum mechanical phenomena, so which is involved to communicate for one with other. Okay, so to communicate one with another they have quantum mechanical signals. Okay, that I can say, but it is out of your syllabus. You learn in your higher classes. So there is something called exchange interaction. So which happens among them. Exchange interactions. Okay, exchange interaction that happens among the electrons. This spins. Sorry, spins. Okay. So what we have learned in ferromagnet, there are permanent dipole moment. Not only that, dipole moments will align in the same direction for a particular region. Okay. So those regions are called, those are microscopic regions which are called domain. And each domain has a size or dimension of 1 millimeter, and they contain, each domain can contain of like almost 10 to the power 11 atoms in each domain. And if this is the case, then for each domain there will be huge net dipole moment. But still, see, I'll just give you some example of ferromagnet like nickel, cobalt, then iron. But still, these uh, materials, you know, they don't show their magnetic property. If you just bring one nickel with another nickel piece, they don't attract each other. Why? They have, I told that they have magnetic domains, and each domain there are almost 10 to the power 10 atoms. So they have huge net dipole moment, but still they won't attract each other or they don't show magnetic property. Why? Because in absence of, when you don't have any external field, in absence of external field, what happens? These domains, you I had drawn, you might have noticed that some domain will be having dipole moments, net dipole moment in this direction, some will be this direction, some will be having net dipole moment this direction. Okay, and some may have this direction. That means these domains are individually magnetic, but these domains, all the domains are not aligned in the same direction. You look, this is directed in this direction, this is lower, this is somewhere this direction, and this is in the right. So you can see these domains are actually random. Domains, magnetic domains are random. magnetic domains are random. That's why net dipole moment, net dipole moment, this is not exactly zero, but very less, very less. Less. Net dipole moment will be less, comparatively less. Okay, nearly zero actually, nearly equal to zero, but not exactly zero. It has some magnetization, but it is very less. So we may not be able to feel it. But if you apply external field, external magnetic field B0, then these domains, these domains, what they will do, they will orient themselves in the field direction slowly. Okay, and these materials can be easily magnetized because they have already domains. So what happens, these domains will be, suppose in this direction magnetic fields are in the magnetic moment here, here in this direction, here in this direction again. Okay, maybe they are in this direction, like this. So what will happen, when you increase the field slowly, and obviously at low temperature, so where the thermal energy for their random motion is very less, or comparatively like compared to zero at low temperature, almost some 5 to 2 Kelvin temperature. Okay, thermal energy can be neglected, or very less compared to their exchange interaction or exchange energy. So what happens in this case when you apply the field? See, if I take a case here, so see in this material what will happen in this direction, in the direction of field, the domain will increase in the direction of field, and the domain which are opposite to the field direction or in other direction, their size will decrease slowly. This is called domain wall motion. So see in these are actually in the direction of field, so this will grow and other domain will be shrink. Okay, other domain will be shrinking and this domain will actually increase. Okay, this domain will slowly increase, other domain will shrink. Okay, so at certain time what will happen when you apply very large field, and see sometime what will happen, all the domains will merge together. If you further increase the field, all the domain will merge together and giving rise to magnetic dipole moments in the same direction as the field. Okay, all the domains will be merging together, and this is the condition of saturation magnetization. This is called when all the dipoles are aligned in the field direction. This is called saturation, and here you will get the maximum magnetization for a ferromagnetic material. Okay, so actually there are different phenomena. First, it will be domain wall motion. If you apply field slowly, domain wall motion, and then second will be actually if you further apply stronger field, this is low field. At low field, that means the wall will actually the domain size will increase for the domain in which the dipole moments are in the applied field. That domain wall will actually will be having like having increasing area. Actually that domain will be having increasing area slowly compared to the other region. Okay, that is called domain wall motion. But if you increase very large field, then what happen, directly domain will rotate, domain rotation. Okay, domain rotation also happens, domain rotation, directly domain will rotate, the whole domain itself will rotate to this direction. Okay, if the domain suppose it was in this direction, okay, before your application of field or at low field, if we apply a very large field, then directly it will rotate to the, so see in this direction it is rotating. Okay, So it will rotate directly towards the field direction. So this is called domain rotation. So there are two phenomena generally happens if you apply like field at low temperature in the ferromagnetic material. Okay. So this is about ferromagnetic material and how, like, what is the origin of magnetization in ferromagnetic material, and how if you apply external field, how a ferromagnetic material becomes a magnet. Okay. Now look, ferromagnetic material, they have actually permeability very large. Okay, very large. Sometimes it is mu r can be as large as 1,000, even more than that. Okay, for iron, nickel. Okay, these are very good ferromagnet. For them, actually, the relative permeability is very large. Okay, compared to para and diamagnet. For diamagnet, it is nearly 1. Paramagnet, it is greater than 1. In paramagnet, actually, diamagnet, it is 1 or less than 1. Okay, but in case of paramagnet, it is slightly greater than 1. But in case of ferromagnet, this is ferromagnet. Okay, ferromagnet is short, in short form it is denoted as Fm. So for them, actually, permeability is very large. That means what? If you keep a ferromagnetic material inside a magnetic field, what will happen? So it will try to concentrate all the magnetic field lines, almost all the magnetic field lines inside it, and try to get induced by the field. Okay, try to get induced by the field. So it will try to concentrate all the magnetic field lines outside. So in case of diamagnet, magnetism outside is greater than magnetism inside. So this is for dia. In case of paramagnet, magnetization outside is less than magnetization, or I can say induction in okay, magnetization inside. Okay, but in case of ferromagnet also, in case of this is para, ferromagnet outside is much less than, much less than m inside. Okay, this is the case. That's why, see, irons, if you just take any iron piece near a magnet, then that is strongly attracted. That is strongly attracted. That means ferromagnetic material can be easily magnetized, and also the strength of the magnetization will be more because it concentrates all the field lines inside it. Okay, this is the case. And yes, so in this case also, ferromagnet also, for case of ferromagnet also, it has a dependence with field and with temperature. It depends on actually T minus Tc, inversely proportional to T minus Tc. So what is this Tc? I told that at low temperature, if we increase the magnetic field, applied field, then all the dipoles will be oriented in a same direction as the field. But if you increase the temperature slowly, what will happen? After certain temperature, what will happen? Magnetization will drop. See, these domains will be actually disappeared. Domains will be disappeared, and all the, see, at low temperature I had domain like this. Okay, but if you increase the high, like increase it to high temperature, this is at low temperature. Okay, in a material there are various domains like this. But if you increase the temperature, T is very high, then what happens? All the domains gets broken, and the actually magnetic moment or the dipole moments will be disintegrating from each other, and they will be totally random. And this situation is called actually paramagnetic situation, and that happens after a certain temperature. Okay, after a certain temperature, that is called critical temperature. Okay, critical temperature. And the theory for ferromagnet was given by Weiss. So this is actually Curie Weiss. If I write See, this is if I write in combination and I write in terms of chi, it will be c by t minus. Okay, sorry. This will be equal. Okay, equal c by t minus Tc. This is called critical temperature. What is this critical temperature? This is the temperature if you suppose have a ferromagnetic material, and from low temperature if you increase the so T is equal to 0 to this. So if you increase the temperature, after certain temperature it will become a paramagnet. So I'll draw the graph. So it will be, it will be like this. Okay, this is the Tc. Suppose this is Tc. See, this is ms. Okay, this is magnetization versus temperature. Okay, this is Tc. If I draw chi versus T, look what happened in case of chi versus T. Actually, it will be like this. See, this after this, actually it will not go 0 directly. It will be like this. Okay, so like this. This is your Tc. This region is actually ferromagnetic region, and this is actually paramagnetic region. Okay, this is chi versus T, or M versus T also will be the same type. Okay, this temperature is called transition temperature. Actually, this is called phase transition temperature. Okay, this is called transition temperature. Critical this, and also critical temperature. So why this temperature is important? Because below this temperature material is ferromagnet, and above this temperature, see, this is above this temperature Tc, the material becomes paramagnet. Okay, that's why it is important temperature, and it is called critical temperature. Suppose you are decreasing the temperature from very high temperature, then once you reach at this Tc, below that the magnetization will increase like anything. Okay, and at very low temperature it will saturate also. This is called saturation magnetization. When further increasing temperature, decreasing temperature or increasing field, the magnetization will not increase. Okay, this is called M. This is chi s. Here I can say ms. Okay, this is ms, saturation magnetization. So these are two graphs. Okay, so I hope you have understood this. This is called actually Curie-Weiss law. Curie-Weiss law. Curie-Weiss law. All right. So we have learned what is ferromagnet and what is the origin of ferromagnetism, etc. We have learned. So I look how many people are still remaining. So this is about ferromagnet and paramagnet. So can I continue another 5 minutes, 5 to 6 minutes? Pujita and Chandana. Others have already left. Or I'll stop it here. You can write in your chat box. Can I stop it here, or I'll continue for another 5 minutes so that I can finish this chapter? Pujita, you wanted to say something, but this Deepa, okay, Deepa, I could not hear you properly. Okay, what about Chandana? Okay, just yeah, I think I'll do one thing. I'll stop it here because others are also not there. I'll stop it here. What I'll do in the next class on Wednesday, I'll take up few numerical as well as some competitive exam type questions on this particular chapter. Just before that, I'll take 10 minutes to discuss the remaining portion. Okay, the hysteresis loop. I'll discuss the hysteresis loop on that day, Wednesday, and I'll take up uh, few numerical problems as well as conceptual problems which are being asked in various competitive exam. Okay, so I think I'll stop it here today. See you all on Wednesday at the same time. Okay, good evening then. Yeah.
Okay, sir.
Okay then. Bye.